Hope you're doing good. So, today we'll be discussing a topic which is a subject in your fourth semester BTech in most of the branches like computer science, um, IT, and branches like AIML and other derivatives of computer science. And it's a really interesting okay, not a chapter, it's a subject, and was personally my one of my favorite subjects back in the day. And let's begin with it without any further ado. So it's called Formal Languages and Automata, which we more popularly call as Theory of Computation or TOC. So, okay, my inspiration for this particular video was making it a bit interesting, making it a bit, you know, I should say, interactive kind of. Because when we study in the classes, I know like all of the people, no, none of the people, none of the students are listening, and even the way it is taught in the classroom, as the name itself suggests, it's a theoretical subject. तो पढ़ाया भी उसको वैसे ही जाता है कि teachers are simply reading out. They do not introduce us to the whole idea of this subject, and why at all do we even need to study computation in a theoretical way. What's the theory behind the whole computation thing, which is such a practical thing going on, but there's still something theoretical. And as we'll progress, we'll find out that there are a lot of things which are abstract, which are actually not going on, but and they're abstract. That's why we call it a theory. But still, the way things happen practically can be very, very like completely made an analogy with the with the ways we are studying it in the theoretical part. So which is why I think which it's important to make it very interactive. So for that, I have brought yeah, firstly the definition that I found to be the most amazing one. Of course, I ChatGPT'd it, and I actually asked it what really is theory of computation. It told me it gave me a lot of definitions. The one that I like the most is this: it is the physics of computer science. And the way in physical world, we do not really have formulae, we do not really have all those things, the way we visualize it in physics. But physics is an amazing tool. It's the closest to a tool, if at all we have one, to actually portraying physical and practical things going on paper, or maybe in a very structured format. So I think this is such an appropriate definition for TOC, that it is the physics of computer science. Just the way physics tells engineers the laws of nature, TOC tells programmers the laws of computation. And just like physics, you can't travel faster than light, TOC tells us some problems that cannot be computed. Now, again, the moment I read this, that this is the main thing TOC tells us, I went on to asking GPT, give me some examples of the problems that cannot be computed. Now I found out these three, and see, I think these are quite complex, and we will be able to fully understand them only by the end of our whole course on TOC. If at all I make one, just check out if there's a playlist by the time you're watching the video. But for now, I think this was important to discuss, that what exactly are the problems that cannot be computed, and I think we'll be only be able to figure it out completely by the end of the course. But we'll just skim, uh, we'll just go through and get a kind of idea of the problems that cannot be computed. And it's firstly, it's very striking, it's very thought provoking that computer is such a powerful machine, but still it at the end of the day, it's a machine, and it has its own limitations. So let's come on to the first limitation, which is the halting problem. The halting problem, discovered by Alan Turing, asks, given a program and an input, can we determine whether a program will stop or run forever? For example, there's a program that checks if program B will stop. Now this guy Turing proved that no universal program can correctly determine this for all the programs. So we cannot determine if a program will ever stop or not, or will it continue forever, will it run forever. So such a program like program A does not exist. It cannot exist. Maybe towards the end of the course we'll figure out things in a more mathematical and a more structured form, but just to get an idea of what this subject has to offer us, and to get that curiosity in you, that what endeavors are we likely to expect uh, during the course of this studying the subject. Second program is the program equivalence problem. Given two programs, do they produce exactly the same output for all the inputs? For example, there's a program that sorts numbers, there's another program that sorts numbers using another algorithm. Now, we might want a program that checks whether they are perfectly equivalent or not. Now, when it comes to sorting, I have actually studied multiple languages, and some of the popular sorting algorithms are merge sort, bubble sort, selection, insertion sort, a lot of these. So we might want a program that would check whether all of these kind of sorting algorithms, for example, let's say for example merge and bubble sort, are they, like, algorithm wise, are they perfectly equivalent or not. But in general this is not computable. Now, to me this was the most thought provoking, most striking thing when I first read it, that we cannot really find whether these are perfectly equivalent or not. And when I thought about it, I actually found out that, of course, like, the way they work, they produce the exact same results, that is a sorted array, but the way they work is completely different. So they aren't equivalent in the way they work behind the scenes. And then third is the post correspondence problem, which asks whether a sequence of string pairs can be arranged so that the top and the bottom strings become identical. It looks somehow like this, somewhat like this. And again, this is again a program, the kind of problem that is not computable. So yeah, when I actually went through these three examples, I thought that okay, there are going to be a lot of things that uh, when I was learning the subject, I wouldn't recognize this. So I wanted a kind of a roadmap, and this is something a lot of people, they do not actually talk about this in any subject. They do not give a clear roadmap for a beginner before starting any topic, and the roadmap should simply be a brief introduction of the kind of things we are going to encounter. So here's a complete flowchart sort of. What can computers actually compute is the whole motive of this TOC. And under this we have two questions: how do we model computation, and are there problems that computers can't solve? Now under this question we have something called as the design models, under which we have two subcategories. We start with the simplest machines a computer. This is basically the flow in which we are going to study this subject, the flow in which TOC will open up for us. So we start with the simplest machines a computer could be, and then we study languages problems as sets. So again, this is something that a lot of people would be familiar with. Isn't this programming, like finding logical algorithms for each problem? So study languages problems as sets, the way we actually solve a lot of problems. And under the design models we have two categories, as I said. Now this one is quite familiar, as I said again, and this basically talks about how do we solve problems using machines. And then we talk about the kind of problems that machines cannot solve, and for that we need to discuss the simplest machine that a computer could be, and the simplest, also the kind of problems that this simplest machine can solve. But before going ahead, let's come back to this. Are there problems that computers can't solve, and for which we find the limits of a computer? Now, the first simplest machine is the finite automata. Automata basically stands for a machine, and these are the simple machines with no memory at all. Now, the problem that we ask is what patterns can such machines recognize? And then we come to the regular languages under which we study these three topics, which I think we shouldn't be discussing today. Just get a reading of them. But there are some patterns that cannot be recognized. Again, there are some patterns, and then through these we get to the regular languages. But then when we don't find any patterns at all, for example, nested structures like parentheses, we need a stronger machine, for which we get to the second kind of machines. First was the finite automata, and second is the push down automata. Now here you may note that finite automata, as I mentioned, has no memory, while push down automata has a stack memory, as I've written here. Push down automata is a machine with a stack memory. Now under these we study the context free languages. Again, when we study the kind of problems that based on limitations of a certain generation of computers, or certain generation of machines, we get to the kind of machines, and we discuss three types of machines that we'll get to towards the end. And then after this we get to the languages part, which suggests that for every sort of machines, there's a specific language that we need to follow, there's a specific grammar that we need to follow for that language. Now, still not enough for all the computation, and hence we come to the most powerful model, which are the Turing machines. Now we ask the deepest question: Are these problems even Turing? Are there problems even Turing machines cannot solve? And then, we have the three problems that we discussed in the beginning. And then the final questions among solvable problems, which are easy and which are extremely hard. And under that, we talk about the computational complexity. So I think with the help of this flow chart, you would have got a basic idea of what TOC is. So with this, we come to three basic concepts, basically pillars of theory of computation. And as I've mentioned, these three concepts, three pillars, are languages, grammars, and automata. Now, we'll come, this is where your, part which is very, very relevant for your exams. This is where it all starts. I was just creating a background so that you have a great idea of what the subject has to offer us. Now, from here, I believe that you will be getting a content that is like completely as it is relevant for your exams. So firstly, there are some symbols. This sigma represents a set of symbols, which is the alphabet. Now, a finite sequence of symbols from alphabet is a string. So if you make a finite sequence of certain symbols, like there are symbols like A, B, C, and then if you make a finite sequence, you get this. This is called a string. Now, a set of strings on alphabet sigma is called a language. So we can actually make a lot of such strings. Okay, I shall erase this. B, C, D, a lot of anything. And if I make a set of these strings, we call it a language, which is okay, we'll come to that later. So let's say, for example, there's a set ABC, there's a string. As I already discussed, these can be the possible strings. Okay, no, EFG is not a string that can be made out of this set, but it's a general example of a string. And here is a general example of a set of strings, which is a language. Now, we come to an example which is quite important. There's a sigma, basically a set of symbols, which is an alphabet. So we have been given this sigma. Now we have been asked to define a closure of sigma. A closure of any symbol is represented by this this characters asterisk, and it refers to a set of all the possible strings that can be formed from these two symbols. So if we do not pick A and B, neither A nor B, we get an empty symbol. If we pick A, we get A, we pick B, we get B, we can pick A twice, we can pick B twice, we can pick A once and then B once, we can first pick B and then pick A, we can pick A and then again A and then B. So there can be infinite kind of combinations that we can form on any given set, and hence a closure of any given set is an infinite set, which is something that I've mentioned, so you may note it down. So that a closure on any given set is an infinite set. Now, a sentence is a string in language L that will, a string in language L will be called a sentence of L. Let's see some examples. So this this is a set, and this is a language on sigma. So since it is it is a finite number of sentences, we call it a finite language. Now, a subset of sigma star is a language. I previously, made some mistake in writing. I probably would have written this, but this is completely wrong, which is why I've corrected it here so that you just remember it. That language is a subset of sigma star. All the different kinds of strings that can be formed on any given alphabet, if we make a set of all of that, which will be an infinite set, but we pick a subset of that, we can call it a language. So let's see some examples of a language on alphabet. A, B, B, C, D, F, Z, S, P, anything. This is a language, and maybe we can call it L1. Another one, uh, anything like P, 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 T, W, S, anything. This is another language. So there can be multiple languages, but the closure thing, I actually can never write the whole, set, because that is an infinite set. So we have been given an example. This is a language on sigma, and okay. So we have been given another example. L, which is an infinite language. The definition of L is A power n, B power n, for n greater than equal to 0. So this is also a language on sigma. Now there are three kind of strings that we can take an example, and we'll try to find out if these strings uh, belong to this language on a language on sigma or not, which we define with L. The first string is A A B B, second is this A A A A B B B B, and then we have A B B. Now the first one, A can be said to be raised to the power of 2, and again B also can be said to be raised to the power of 2, because there are two A's and two B's. So basically number of A's and number of B's should be the same, which is n. So anything, any kind of string which satisfies that property will be a part of this language. Now this have A and B's, number of A and B, it has equal number of A's and B's. So this string 1 is it belongs to this language. Same for this, it has equal number of A's and B's, so this belongs to this language. But then in this, the number of A's and B's are not equal, so this does not belong to this language. So that was it. Then we have the second pillar. Now this is something kind of important, and again, before starting with grammar, hear me out. um, so what happens in a computer is that everything inside a computer goes from multiple states, from one state to the another, and you're given some inputs, and the states give out some outputs. These outputs are further inputs to the other states. So that is what goes on behind the scenes. Now everything that goes on behind the scenes is actually um, expressed in the form of a language, which necessarily might not be an English or a Hindi language, or a French or a Spanish language, which again might not be necessarily be a programming language like Python or Java or C++, but it's a different kind of language that we'll find out. And it also, it can be just defined in any way possible. And to define that language, there are certain rules, and that set of rules is basically called a grammar. So now grammar G, everything in TOC will have a symbol. So this grammar has a symbol G, and it's a quadruple, which means that it's a tuple of four elements: V, T, S, and P. Each of them stand for something. V stands for a finite set of objects which are called variables. T stands for a finite set of objects which are called the terminal symbols. S stands for a finite, it belongs to V, which is this variables thing, and is a special symbol, which is a start variable. And P is a finite set of productions. So if we define these four things, we get a grammar, which is a set of rules. And if we define a grammar, we can actually derive a language for that particular grammar. Now, these four are the most, like, this is at the heart of a grammar, heart of a language. I have also written it heart of a grammar thing here, but okay, we'll find that out. And why this production thing is at the heart of grammar, because it's the most important one. So we start whenever we have to generate a grammar. We start with a start variable, which is the S, which must belong to a set of variables, which is the finite set of objects, and there must be some terminal symbols, the one that we finally get. When we are deriving a grammar, deriving a language, there are multiple steps, and in the final step, the set of symbols that we get are called the terminal symbols. Now again, in every step there would be terminal symbols, but the one that will actually define the language will be the one that we get at the end of all our steps. And P is the finite set of productions. How do we get there? So I hope you would have got a brief idea of all of this. And now coming to the most important one, which are the productions. Productions are at the heart of a grammar, basically the production rules. Now a very very important, like, golden line: by applying the production rule in a different order, a given grammar can normally generate many strings. The set of all such terminal strings is the language defined or generated by the grammar. And now the mathematical definition in the set form of this particular line that I wrote here: let G, which are these four symbols, let G be a grammar. Now a language which is defined on G, or generated by this grammar G, is defined by this: omega is a subset of T closure, or T star, and S uh, transforms to omega S, sorry, the closure of S transforms to omega. Now this is a language generated by G. Now if omega belongs to this language, omega is basically the final terminal symbol. Then this whole sequence, this sequence that we'll just figure out: S, you know, derives omega 1, which again derives omega 2, which derives omega 3, and so on till omega n, which again derives omega. This basically is the whole derivation of the sentence omega. This omega is a sentence omega, and this belongs to language LG. So that was it. That was it for this particular video. We have, I hope that two topics that we were supposed to discuss today. One is the language, and second is the grammar. I hope these two are clear to you. And we'll, even if like you understood only 20% of it, it's fine, because in the forthcoming videos we'll do a lot of questions, a lot of examples, a lot of topics ahead of like these topics, which will make the foundation, the basics, even more clear. And I will keep on reiterating the foundational topics time and again, so that they just keep on, you just get a very you just keep are able to keep up with the previous topics as we go ahead. And these are the topics that we will discuss in the next few sets of videos: deterministic automata, non-deterministic automata, next state of the transition function. Yeah, so thank you for watching this video. Have a good day.